imagine witnessing a cosmic explosion mere hours after it erupts, a thrilling prospect that could revolutionize our understanding of the universe. Supernovae, those phenomenal stellar outbursts, capture attention as dazzling flashes of light emerging in places previously enveloped in darkness. They leave astronomers scrambling to catch these elusive events before vital clues fade away. But here's where the drama unfolds. A new rapid response protocol now promises to pin down supernovae within hours of their eruption, opening a door to unprecedented scientific insight. Intrigued yet? Most people never realize just how much happens in those first fleeting moments. Here's the story. Every supernova signals a spectacular death in the life cycle of a star. Traditionally, these explosions were notoriously tough to study due to their sudden and unpredictable nature. A star seemingly invisible one night can blaze gloriously the next, a cosmic fireworks show with no warning. Until recently, astronomers often found themselves days or even weeks late to the party, missing those crucial early signals. Advanced non-stop sky surveys are changing the game, catching new supernovae almost every day. But early detection is only half the battle. Effective protocols are essential to ensure scientists can track these events before their secrets slip away. And this is the part most people overlook. If we miss those first hours, we lose access to some of the universe's most potent mysteries. A research team led by Luis Galbani at Barcelona's Institute of Space Sciences set out to solve this. Their newly released pilot study outlines a technique designed to capture the earliest possible observations, ideally within 24 to 48 hours of a supernova's first glimmer. Published in the Journal of Cosmology and Astroparticle Physics, their methodology could soon become standard practice. Why is early observation so important? Right after the blast, clues about the original star and its immediate surroundings are still unmistakably present, enabling scientists to distinguish between various theoretical models, estimate physical parameters, and analyze the local cosmic setting. The faster you tune in, the richer the data. Let's break down the types of supernova. The first, called thermonuclear supernova, involves stars whose initial mass didn't surpass roughly 8 times that of our Sun. These stars end their lives as white dwarfs, old, compact remnants that don't produce heat in their cores. Fascinatingly, white dwarfs can persist in a stable state for eons, held up by a phenomenon known as electron degeneracy pressure. But there's a twist. If a white dwarf is part of a binary star system, it may greedily accumulate matter from its companion. Eventually, this tips the balance and pressure skyrockets, leading to a runaway explosion, a supernova. The second category, core collapse supernovae, originating from stars far heftier than 8 solar masses. These giants shine thanks to nuclear fusion at their cores, but as they burn through progressively heavier elements, fusion can no longer sustain their gravity. When this balance fails, gravity forces the core to contract rapidly, ramping up internal pressure and sparking a dramatic explosion. Now, here's the controversy. Observing supernovae right after they erupt is a real challenge, and opinions swirl on whether astronomers have been missing out on game-changing insights by relying on delayed discoveries. The immediate aftermath holds vital information that can fundamentally shape our models for how stars die. Do too many studies overlook the earliest phase just because it's harder to catch? To overcome these challenges, Galbani's team tested a high-speed procedure using data from the Gran Telescopio de Canarias, GTC. They focused on 10 supernovae, half thermonuclear, half core collapse, which they managed to observe as early as 6 days post-explosion, and in 2 thrilling cases within just 48 hours. Here's how they did it. The team constantly scanned sky images for new, bright objects where none existed before, specifically inside galaxies. If something pops up overnight, it's flagged, and the GTC's OSIRIS instrument is immediately triggered to grab a spectrum, providing clues about the type of supernova. For instance, if hydrogen appears in the spectrum, it's likely a core collapse supernova, information that's invaluable in categorizing and understanding these objects. But the story doesn't stop with spectra. Galbani's approach also grabs photometric data from other powerful surveys, like the Zwicky Transient Facility, ZTF, and the Asteroid Terrestrial Impact Last Alert System, ATLAS. These observations trace the rise in brightness, sometimes revealing peculiar bumps suggesting the explosive demise might have engulfed a companion star. And most people miss this detail. Cross-referencing different telescope datasets can uncover subtle features you'd never catch otherwise. What's really exciting is that the protocol developed in this pilot study proved it's possible to collect crucial data within hours of a supernova's eruption. Galbani and T are optimistic. Tightly coordinated rapid response programs could routinely bring in spectra within a day, especially as formidable surveys such as the La Silla Southern Supernova Survey, LS4, and the Legacy Survey of Space and Time, LSST, ramp up operations in Chile. Controversy alert. Is the astronomical community ready to prioritize and invest in more aggressive, rapid response protocols given the technical and logistical hurdles? Or are traditional, slower studies enough to decode the secrets of stellar death? So what do you think? Should catching supernovae in their earliest moments become standard practice? Or do you believe later observations are just as valuable? Does the promise of rapid data truly outweigh the resources required for instant follow-up? We want to hear your take. Share your thoughts, questions, and debate below.